Alright, welcome to Carbohydrates Chapter 16, Part 3. So this lecture we're going to be talking about our oligosaccharides and our polysaccharides. So what is an oligosaccharidide? It is the short polymers containing 2 to 10 monosaccharide residues. So we talked about monosaccharides in our last lecture, and we said that each one of these rings was going to be a monosaccharide. So now we're going to start connecting these residues. So that's another way to say the monosaccharides is a residue. And we're going to put them in chains. And these chains that are 2 to 10 of these monosaccharides are going to be an oligosaccharide. Anything beyond 10 we're going to call our polysaccharides. Now to connect these long chains or these residues together, we're going to be calling them the glycosidic bonds. And a glycosidic bond is just an ether linkage that is made when an acetal is by reacting a hemiacetal and a monosaccharide with a hydroxyl group and on another sugar. So in other words, I've got this hemiacetal group here, I've got the alcohol here, and I'm going to basically create water, because notice water is the byproduct. I'm going to pull off another water and connect what's left. So this is very similar to our dehydration reaction, since I'm literally dehydrating it every time I connect a residue. I'm producing water, taking away water from here and producing it over here, and then connecting what's left. Now you may have noticed a couple slides ago that there were a couple different ways that we can link this. We can link them from the bottom, or we can link them from the top. So we got to name or define what type of linkage that we have. So we called our hemiacetal, if our hydroxide was on the bottom of the ring, we called it an alpha. So we have our A for alpha. Then we're just going to label where they are connecting. So on the hemiacetal, it's connecting at the first carbon. At the other residue, it's connecting at the fourth carbon. So we're going to call this an alpha or A 1,4-glycosidic bond. Just as a reminder, this is forming because I'm going to take away that OH and H and produce water here. Then once water is formed, I get a linkage between the residues. So that is what we are naming, is that linkage here. So we just looked at an alpha bond, but here's another example of an alpha, and we'll look at a beta. So we said that our bond was going down, so that means it's alpha, and then it's got 1,4. For a beta now, it was on top of our hemiacetal ring, and it's still connecting at the fourth carbon. So now this is a beta 1,4 disaccharide, or a beta 1,4-glycosidic bond if we're just talking about the bond. So let's look at a couple examples. So cellobiose is an example of our beta 1,4-glycosidic bonds. So this is a disaccharide formed when polysaccharides of cellulose are broken down. So when you break down any kind of cellulose, especially in plants. But because it's in plants and from a cell wall, we actually cannot hydrolyze this. So even though this is carbohydrates, we don't get any energy from this because we lack the enzyme to actually break this bond. So because we can't break that bond, we can't break these residues down, we don't get the energy out of it. However, plants and other animals actually do have the enzymes to be able to start breaking these down. You think of like cows. Cows eat a lot of plants. So they need to get this energy or to be able to break these bonds. So they do have other enzymes than we do to be able to break them. So talking actually about the linkage though, I have my hemiacetal. The OH was pointed up, so it's beta. And this one is also connected to the fourth carbon on the second residue. So here's another oligosaccharide example that I'm pretty sure you've all heard of, are lactose. So you think of people that are lactose intolerant. Well, let's take a look at why. So lactose is a disaccharide that's found in milk. So this lactose, once again, just like a lot of our other ones, It is, our hemitacetal is pointing up, so it's beta. It's attached to the first and fourth carbon, so it's a beta 1,4 glycosidic bond. Sounds a lot like our cellulose, right? So why is it different? What's the only difference between the two? If we looked back at our cellulose, this OH here, right here, is actually below the chain, and it's above the chain in lactose. So we actually are able to connect to this oligosaccharide and digest it, as long as we have the enzyme. However, a lactose intolerance then is the inability to hydrolyze this lactose due to an enzyme deficiency. So whenever you see like people taking some kind of supplement to be able to have lactose, that supplement is an enzyme that they're taking so that they can hydrolyze this bond and actually get the energy out of it. A lot of times when we can't digest something, our body reacts to it in a not good way, so you get side effects when we can't hydrolyze things or we can't break things down. So that's why people don't feel good when they have lactose if they have lactose intolerance. Alright, so let's look at a more interesting example of this glycosidic bond. So we've actually got sucrose here. So table sugar. This is what you go to your pantry and you eat. So you go to the store and you buy sugar. It's sucrose. So what is the sucrose? So sucrose is a 2-residue oligosaccharide. The catch with this one is that there is no hemiacetal because it's actually acetal now, since we are actually connecting both of these residues at the hemiacetal point. So if we look at this first one, we see that it's pointing down, so it's alpha, and it's attached to the first carbon. So it's an alpha 1. Here, I'm also at the acetal group, and it's at the second carbon, and it's pointing up. So it's a beta 2. So this is an alpha beta 1,2 glycosidic bond. So we can't connect them at any point. We can even connect 2 different size rings. We're just going to need to name exactly where they're connected and if that alcohol that was basically dehydrated, pointing up or pointing down, or above or below the ring. Or I guess beta is above, and below the ring. Another interesting note with these oligosaccharide chains is that they are also in equilibrium with their anomers. So although this glycosidic bond never changes, this doesn't change, but the end that can, or the other acetal or hemiacetal end to it, can actually change. So right now I've got it in the alpha anomer, so that ring can still open and twist and form the beta anomer. So we can open up the hemiacetal portion that's not connected, but those glycosidic bonds are not going to change. So if you've noticed so far, we've only looked at pretty much disaccharides, so 2 saccharides in our chain for these oligosaccharides, but those are actually the most common because they're normally the easiest to break down. So those are the ones that we are most familiar with and that we interact with the most. But there are obviously other ones that have longer chains. So we have our raffinose. These are our 3-chain or 3-residue carbohydrate or 3-residue oligosaccharide. So we've got an alpha 1, and then this is attached to 1, 2, 3, 4, 5, 6. So this would be an alpha 1,6 bond. Here we would have our 1, 2 alpha beta glycosidic bond. And these ones are very similar. So this is also another 1,6 alpha, another 1,6 alpha, or alpha 1,6, and our alpha beta 1,2. Note that we said that we don't interact with these ones very much. It's because they're indigestible. We can't digest either of these ones. It's because we don't have an enzyme that can break a 1,6 glycosidic bond. So especially an alpha 1,6 glycosidic bond. We can't break it apart, so even though it's found in, we saw peas and beans, we don't get the energy, or all of the energy, out of those bonds because we can't break apart those 1,6 glycosidic bonds. So another one that we can't break apart is actually what we use for BINO. So they are indigestible since we can't, so like you think of beans, because we don't have that 1,6 glycosidic bond. But BINO is actually an enzyme that helps us digest some of those bonds. So it's basically a supplement enzyme that helps us helps us to break apart those bonds. So instead of getting the byproduct of gas in our intestines, if we take this enzyme, we don't get that gas because it's able to break apart those bonds. Our body's able to digest it, and so we don't get the side effects of not being able to digest something. You'll notice that a lot of times that when you eat anything that has no fat or very, very low fat foods, it's because they were replacing it with something that's not digestible to our bodies. So a lot of times those foods actually produce a lot of gas. So if you go and try to go buy no-fat potato chips, they may not do great to your intestines. So you'll have less calories, but you still won't feel very good because you'll still be all gassy. So it's interesting that we have other products that can prevent the gas from forming, but we also sometimes eat products that make the gas form, since that's what we don't want, the calories associated with being able to break apart those bonds. Another type of oligosaccharide we can look at are glycolipids. So these are sugar-containing lipids, so sugar-containing fats that are going to be present on nerve cell membranes and actually are present on most cell membranes to be able to provide stability, and they serve as identifying markers on cells. So they help cells identify each other. So that's great for our immune responses because they can identify whether a cell should be there or not. So these are hemiacetals of sugars and sugar residues connected to an alcohol group by a glycosidic bond. So we're using that hemiacetal right here, and instead of attaching to another residue, we're attaching to a lipid, which is what we're going to be talking about next chapter. Alright, so we've been talking a lot about sugars and sugar residues, but what makes it kind of taste sweet, and how do we know how sweet it is? So let's take a look. So sweetness is rated in comparison to sucrose, so into just our normal table sugar, which they artificially assign to a sweetness level of 100. So sweeteners used in our foods are divided into two classes, natural and artificial. So natural and our natural sweeteners are sugars or sugar derivatives, and artificial sweeteners may bear no similarities to sugars, but they somehow still taste sweet onto our tongues. So here are our natural sweeteners. So we think of Splenda. So think of our sucralose or sucrose. So sucrose is our sugar. We have OHs here, which we can break down in our body. Sucralose, which is Splenda, has chlorines there instead. So without having the hydroxides there, our body can no longer process the sugar, so that's why it's a no-calorie sweetener, because we can't break it down to get the energy out of it. But notice that they do look very similar, so this would be still considered a quote-unquote natural sugar. That's why you could say it's made from sugar, because it's derived from sugar, and it looks very similar to sugar. The catch is, just like our no-fat Pringles or no-fat foods or low-fat foods, is that even when you can't process these sugars or you can't process these bonds, there may be other side effects that you don't particularly like. So some people can process Splenda just fine. Some people can process other sweeteners just fine. And you may not be able to. You may get a terrible headache or get terrible gas. it depends on how your body reacts to not being able to process something. So here's a scale of sweetness compared to our sucrose. So these are all natural sweeteners. So fructose, so you think of high fructose corn syrup, right? Why do they add it? Because it's really, really sweet. So when they have something that's high fructose, well, that's because they want it to be super sugary. Whereas we go down our list, so here's our xylitol, this is our alcohol sugar. A lot of times you see this in gum. It's a similar sweetness to sugar. Glucose, that's our corn syrup, so it's tastes a little bit less sweet. Sorbitol is also found in a lot of gums. This is even less sweet, so if you don't want a sweet gum, they'll probably put sorbitol in it. Then we have our maltose, galactose, and our lactose. So even though these are all sugars, they don't really taste sweet. So you don't go drink a whole bunch of milk and go, wow, that tasted like fruit juice, that sweetness from fruit juice. But it does provide a little bit of sweetness, but just not very much. So those were our natural sweeteners. But what about our artificial sweeteners? So the one we're most familiar with is our aspartame. So aspartame is a very common substitute for sugar. So you think of diet soda especially has aspartame in it. Or something that's no sugar added or no sugar, a lot of times there's aspartame in it. Most people process go through and drink aspartame or eat aspartame and they have zero side effects and don't notice it at all. Other people have severe headaches, they have severe intestinal discomforts, but notice the sweetener level. Remember, sugar was 100, aspartame is 18,000. So it's 180 times greater than sugar is. So you don't need a whole lot of aspartame in anything to get that sweet in it. Now here's a common myth that just seems to always perpetuate. So here's your fake news for you. So is there association between artificial sweeteners and cancer? Well, believe it or not, there is no link between our artificial sweeteners and cancer. So you may have heard about it, oh, they're not good for you. Well, it's not that they're not good for you. It's not that they're going to cause cancer. They may make you not feel very good. But there was a study way back when that seemed to show that laboratory animals that had aspartame got a lot of bladder cancer. The catch is that when they did these studies, they injected the animals or had the animals ingest so much aspartame, you'd literally have to drink like 100 cans of soda every day for months to be able to get the same level of aspartame in your body. So there's been no clear evidence of any association with cancer for humans. Now, once again, you eat too much of anything, it's probably going to give you cancer for some reason or another. But everything in moderation, right? So don't go and believe every headline that you see that is a miracle drug or that is going to cause you cancer. And even if there's a study behind it, you still have to go and look at the study and go, well, what did they do? Well, if they inject rats with 100 to 200 times the amount that you would ever drink or ever ingest in a day, well, that study may not actually be relevant to you. All right, what about our polysaccharides now? So we said polysaccharides then contain 10 or more residues of those sugars. So there are two types of polysaccharides that we're going to look at. Homopolysaccharides, which all of the residues are the exact same monosaccharide, and heteropolysaccharides, which they are built from more than one type of polysaccharides. Now, two primary functions of polysaccharides. One is to provide structure, so like cellulose, and another one is to store energy. So if we know that we can get energy from any glycosidic bond, the more we have, the more energy we can get. So we want to connect as many as we can to store our energy. So an example of our homopolysaccharide is cellulose. Cellulose has the same residue every part of the chain, joined by a beta 1,4 glycosidic bond, and there are these long linear chains in our cellulose. However, why is cellulose so strong then if it's just one long chain? Well, it's not actually that it's just one long chain. So we have a bunch of these chains, but they actually can hydrogen bond with the chain next to it. So they actually form sheets. So even though the chains are connected through covalent bonds, the chain next to it then is connected to it with a hydrogen bonds, or a whole bunch of hydrogen bonds. So that is why it's so strong. You think of cellulose being so hard to, rip a leaf up or something like that. It's because it's got all of those hydrogen bonds that it's forming with other chains. So when we think of cellulose, we think of plants. Wood is about 50% cellulose. And bacteria in horses, cows, termites, anything that really eats a lot of plants has a cellulose enzyme, or cellulase. Notice the ASE at the end. ACE means that it is an enzyme to break apart whatever comes in front of it. So cellulase is a enzyme that breaks apart cellulose. So it hydrolyzes those beta 1,4 bonds. So that's why termites can eat wood, or horses and cows can eat all of those plants and branches and such, because they have something that can break apart those bonds, so they can get energy out of it. So another homopolysaccharide that we're going to be familiar with is starch. And starch actually has two different components to it. We're going to look at both. So we have our amylose and amylopectin. We'll see why that starch is such a good way for us to store energy. So some plants, but we also get to use or be able to digest our starch too. So we get to use some of that energy as well. So we think of some starchy foods such as our potatoes. So why can we eat potatoes and get a lot of energy out of them? Well, instead of a beta 1,4 bond, it is now an alpha 1,4 bond for our amylose, so our starch. And unlike our cellulose, instead of those long linear chains, our amylose chains are actually going to be in a helix structure. So they're kind of going around in a spiral instead of being linear. So although this amylose is in a helix, there is still just a big long chain of them. So there are no other connections outside of that chain. They're just coiled around each other. Now the difference between our amylose and amylopectin then, so to our amylose we said this was one long chain even though it's in a helix. Our amylopectin is going to branch. So we have these alpha 1,6 glycosidic bonds branching off of our amylose chain. So because we can have these branches for our amylopectin, molecules end up start looking like this. So we start to curve in, and I've got branches coming off of each of these main chains. Now what's convenient about this amylopectin is that because I've got all of these branches hanging off these chains, there's a lot of surface area, so it's very easily pruned, so that way you can release this energy very quickly. So we can break all of the bonds around the edges and be able to release a lot of energy because of all of the branches that are hanging off of them. Now amylopectin we said was in plants. But what about in animals? That is our glycogen, or our animal starch. So it's very, very similar to the amylopectin, except that there's going to be branching more frequently. So if this was our amylopectin, we now see we have a lot more branches with our glycogen. So in amylopectin, it branches every 25 to 30 residues, but in glycogen, it's every 8 to 12. So, 2 to 3 or 4 times as efficient, or more branches. So that just means that there's that much more surface area for animals to be able to prune that glycogen to get that energy. So there's a lot more storage and a lot more ability to release the energy quickly with using glycogen versus amylopectin. Alright, so another homeopolysaccharide that we actually talked about a little bit earlier is our chitin. So this is that glucosamine that we looked at a little bit earlier. We look at our this chitin and its bonds, or these glucosidic bonds here. See, there's still beta 1,4 bonds, so it's going up, attached to 1 and 4. And because it has all of these OHs on top, they are able to hydrogen bond with other molecules, so of the same thing. So that is why you have these hard exoskeletons of our crustaceans and our insects. It's because of those hydrogen bonds. So it creates a rigidity that allows for the protection of the animal. So notice the difference between these polysaccharides is that they have this amine or amide group here. So we've got our other groups attached instead of our OH group here. The last polysaccharide we are going to look at is finally a heteropolysaccharide, and it's our hyaluronic acid. Now you may or may not have heard of this. It's actually a fairly popular it's in a lot of products. So maybe your mom or grandmother was using like wrinkle creams and such. They a lot of times have this hyaluronic acid in it. It's kind of a lubricating fluid. It's found in surrounding joints, found inside your eye. But you'll see it's also used in skincare. It treats burns, bed sores, wounds, skin ulcers. People or doctors can inject it into your knees to kind of relieve knee pain. So it's kind of a really good biomolecule that just kind of helps us feel better, probably because it's a lubricant. So it just kind of helps our body move a little bit better. All right, so that is the end of chapter 16. So we will start looking at our proteins and our lipids in the next few chapters. And then we're going to kind of put those all together and look at our metabolism.